All right, great. Yeah. And thank you also for the invitation to this conference. It's great to be here, especially that there are so many REU students. It's always exciting to have a lot of students at a conference and in talks. So I'm going to talk about cryptography based on supersingular isogenies. And so I'm going to start a little more broadly by talking about hardness assumptions that are used in public key cryptography, and then mention that just one of the possible ones is cryptography based on isogenies between elliptic curves. And you've already seen some of this in Jason's talk and Gabrielle's talk. There is a very rich structure, both arithmetically and also algebraically. And in particular, there's like an interplay between like being able to phrase problems algebraically, writing things in terms of graphs, and just understanding the geometry. And sort of this interplay is, I think, what a lot of people in this area find fascinating and rewarding, to sort of look at the same problem from different views. And then, since it's about cryptography, also what's sort of known about breaking these systems and what kind of solving what kind of problems that would entail. Okay, so if you are interested in cryptography, that usually involves some computational number theory. And if you sort of look at the standard number theory problems that you've seen probably in some discrete math class, you see like problems over the integers, including computing GCDs, testing whether things are prime, factoring, and then maybe also something like Pell's equation. So these are sort of some of the things you first see when you're doing something just with integer arithmetic. If you want to be more ambitious and actually work with number fields, so finite extensions of the rational numbers that are also fields, then you might run into computing rings of integers, Galois groups, maybe class groups and unit groups of the objects involved. And then sort of with a more arithmetic flavor, if you're interested in elliptic curves, there are a lot of problems there as well. And so, for example, you might want to compute. So Gabrielle mentioned that the points on the elliptic curve form an abelian group, but you may want to know exactly which one you're dealing with. You may want to know what points have finite order, so the torsion subgroup. If you have an elliptic curve that is over a field of characteristic 0, you might have some positive rank, so points of infinite order there. And there are many more problems, including computing maps between curves. So these are sort of, if you ask an arbitrary, like, so if you sort of ask a random number theorist, they would all agree that these are interesting problems, but they're not necessarily immediately connected to crypto. So if you want to look at problems from cryptography, they usually look a little bit different. So there are a lot of number theory problems whose hardness is related to the security of public key crypto systems. And so what happens in public key crypto systems is, so we're only looking at public key crypto here, which is where parties can communicate without having to agree on any secret in advance. So which involves all online transactions, banking transactions. So those are sort of the ones that we're most interested in. And well, so what does that look like? So I'm just gonna like bravely or boldly state here that all known constructions really rely on some hard, believed to be hard underlying problem from number theory. So including like, so maybe people will say, well, what about lattice-based systems? But there you're really working with ideal lattices, which come from ideals in the ring of integers of a number field. So I would like sort of say there's enough number theoretic flavor there that you can like at least classify those again, like that you can say it's related to number theory. So you have some hard problem from number theory. I'll list some a few candidates on the next page, and then on that you build some sort of public key crypto systems. So okay, so what does this look like? So here I've listed a bunch of systems. So probably most well known is RSA, named after Revest, Shamir, and Edelman. And it's based on the hardness of factoring. So a lot of intro number theory classes or discrete math classes list that at some point. Then we have sort of the cryptography based on elliptic curves that we're not really doing anymore, which has as the hardness problem the discrete log problem on elliptic curves. Now we're coming to things that are more current, like LWE, learning with errors, in particular ring LWE, then there's module LWE, and various variations of those problems. And that's related. I'm just going to list one underlying hard problem there. So it's all related to finding shortest vectors in the case of ring LWE in something called an ideal lattice. Then we also have the supersingular isogeny-based cryptography. It rolls right off the tongue. And so Gabrielle talked a little bit about that. That's the problem there that we're interested in is finding isogenies between curves. And then I just threw in a random other one, soliloquy, which is another lattice-based system, and it sort of has the distinction that I will come to in a minute, that it's based on a really interesting underlying problem, which is called the short generator principal ideal problem. It's a problem in which the underlying ideal in the ideal lattice is both principal and has a really short generator. So why is there a third column? Well, so first of all, the hard really has a question mark because it's not really possible to prove that a problem is hard. We're sort of thinking, like, if you just look at RSA, you just think, well, people have tried coming up with factoring algorithms for a really long time, and nobody has come up with a polynomial time algorithm. So that's probably a pretty hard problem. And as you sort of go down this list, these problems have been like sort of not particularly been studied for a really long time. So there's less confidence. Also, the first two problem, factoring and elliptic curve discrete log, and the systems that are based on them, RSA and ECC, those are by far among this list the two most efficient systems. So if those two are so efficient, why would you look at any of those candidates in the rows below that are much, much slower and maybe sort of more like SVP and ideal lattices is still shortest vector problem is studied, has been studied extensively, but not in ideal lattices, and people know much less about how hard it is in ideal lattices. So why would you want to sort of compromise and go to problems that are either have not been studied as hard or lead to systems that are not efficient? And the reason is because we're sort of starting to get more concerned about quantum computers. And so here I should really say not just broken by quantum computer, but by a large-scale quantum computer. People have listed what can be done. Like we've had some talks about like sort of small-scale quantum computers, what they can do. they cannot break RSA. The joke is always that, I don't know, I think of a few years ago when I gave a talk like this, like a quantum computer could factor 15, and like a number theorist from the audience laughed and said like, oh, I can factor 15 as well. We don't need a quantum computer for that. But sort of since like introducing new systems would take decades, just the fact that it might be possible in a few decades is a threat enough that we sort of want to move away from systems like RSA and discrete log that can be broken by quantum computers if they are built to large scale. SVP in ideal lattices is still open. Gabriel in the last talk mentioned that one system was broken that was based on supersingular isogeny, but the general problem is still believed to be hard. And then here is another system where, in order to make the ideal lattice-based system very efficient by assuming that the ideal in question is principal and has a short generator, it compromised the security, and it was possible to like break the system. So that means sort of if you're you certainly want to have your system be as efficient as possible. You don't want to buy something online and have the verification take like 10 hours when you're like clicking buy. But on the other hand, if you're making more and more assumptions and make these things more and more efficient, you may end up compromising the security, which is equally bad. So we're trying to find the sweet spot somewhere between efficiency and security. And for difference hardness assumptions, that may involve, like, that's a different trade-off. For RSA, it's very easy because you can just say, oh, let's make the primes bigger. And that's not very hard to do. You can like generate primes of like arbitrary size. You can like say how many 100 digits you want. It's not a problem. For some of these other systems, it will get much slower. Okay, so what does post-quantum cryptography mean then, which is sort of what this last column was motivating. Namely, the goal here is to develop public key cryptography that is secure even after quantum computers have been built. So even large-scale ones. And so, like I said, broken by large-scale quantum computers are RSA and ECC. And currently still secure are lattice-based systems, LWE, learning with errors, ring LWE, the ring version of it, Michaelis, which we've already heard mentioned in one of the talks, and some of the isogeny-based systems that I'm going to talk about today. Now, at some point, the NSA got worried enough about the prospect of large-scale quantum computers being built that they had a note on their website that said, if you haven't transitioned yet to elliptic curve cryptography, don't do it. Wait for quantum secure recommendations. And so these quantum secure recommendations are supposed to come out of what's called the NIST competition for post-quantum crypto systems. I know we have some people from Maryland here, and like a lot of the people who are at Maryland, some of them are affiliated with NIST. And so the goal is to look now for crypto systems that can serve as an alternate to RSA or ECC. So, and it's really fascinating for me as a mathematician, because usually in math, if the problem hasn't been around for at least 100 years and has been open that long, people are sort of looking at it like, ooh, is this really a problem you want to work on? Is it like serious enough? But the NIST competition only started in 2017. And so this is computer science, cryptography, everything is moving very fast. So initially, there were 69 submissions that were accepted. And already by a month and a half later, a bunch of them were broken. So this is sort of somewhat concerning if you're considering changing all the infrastructure and all the computers that are used everywhere and spending like, I don't know how much money to update everything. That out of 69, 22 were broken pretty quickly. So then they decided to advance 26 submissions to round 2. And all of these submissions are public, a lot of them with benchmarking problems, like if this system is secure, then the following samples that we're posting, these should be hard problems, and then people can run code and try and break it. And so this is how some of these 22 submissions got broken. So these are not theoretical breaks. These are just like someone was able to break whatever they were posting by like coding things. And so code-based system, lattice-based system, and supersingular isogeny-based system survived. There was just one that was psych. Then they got it down to 15 proposals, 7 finalists, and 8 alternates, and then standardized 4 systems, and still gave more scrutiny in a 4th round. And so psych, the isogeny-based system, was the 4th round, was still a 4th round candidate and was considered one of the alternates. I was really excited about that. I had nothing to do with psych itself, but it just it sort of seemed nice that people working on elliptic curves had like some skin in the game with something as important as the NIST competition. But then on July 30th, psych was actually just broken and had to be withdrawn from the competition. So it's sort of, things are moving very quickly, and it's still ongoing. They've asked for more signature proposals, signature scheme proposals. So there's a lot going on, and it's moving very fast, but also things, so things can be broken. And so we definitely need to have people do research on these problems to see how hard they are. And so what is sort of the current state of affairs? So you have like classical polynomial time algorithms. So these are problems that can be solved efficiently, and sort of modular arithmetic is in their elliptic curve if you add points. And now, because of the break of psych, also isogenies between elliptic curves, computing them if torsion info is known. I think you refer to that as level structure in your talk. So that's the same problem. So that has been broken, and it was both a practical and a theoretical break. So they broke the benchmark problems provided by Microsoft from their group, and they also have a theoretical break where they can show that there's an algorithm that solves it in polynomial time. So then there's also quantum polynomial time. Has discrete log in it, factoring, computing the class group, unit group, computing the principal, solving the principal ideal problem, finding a generator of an ideal, and computing endomorphism rings of ordinary elliptic curves is in it as well. So I'm writing these as like 2 blocks of problems based on top of each other, but there's no, I mean, nobody knows if these are actually, if the yellow set is strictly larger than the white set. So it's just, we have a polynomial time quantum algorithm for factoring, but not a classical one. Doesn't mean that one doesn't exist. And then here are a bunch of open problems. So the shortest vector problem in arbitrary dimension is open, also in ideal lattice. So it's isogenous between elliptic curves and computing endomorphism rings of elliptic curves. So if you replace the ordinary with a supersingular, you change from a problem that can be solved efficiently on a quantum computer to one where it's not known how that should work. So there are a bunch of different types of problem, and the ideal thing would be to make some progress in this list here above. and show that some of these really belong into this category, or maybe all the way in this category. I mean, initially, people sort of thought that this problem that led to this break of psych was going to be in this bubble. But it turned out that it didn't even need a quantum algorithm. The break came from like more higher dimensional arithmetic geometry type approach with higher dimensional varieties, which is very beautiful. So okay, so that is sort of the state of where the problems are located. And so like I said before, when I mentioned ECC, elliptic curves have been around for a long time and been used for cryptography for a long time, namely since the early 2000s. So when I first started on working on number theoretic problems with like a cryptographic flavor, it was all the standard traditional elliptic curve cryptography, which is based on the hardness of discrete log, and you have one curve that you're working with, and then you work with multiples of the point and assume that the discrete log problem is hard in that group. Because of Shor's quantum algorithm for discrete log, we don't really want to work with that anymore, but so in this case, the object was just one curve. And so just as to recall what Gabriel had on the slide, if I'm talking about an elliptic curve, I'm talking about points of the form x and y, x comma y, that satisfy this equation, y squared equals x cubed plus ax plus b. And A and B lie in some finite field. So this is the finite field with q elements. And the points on the elliptic curve together with this point at infinity, they form an abelian group. Okay, so here are some pictures of elliptic curves. Just sort of if you change the parameters, you see sort of how the shape changes. And if you pick one in the third row, the second from the left, you get one that's not considered an elliptic curve because it has this sharp spike going out. So that's not a non-singular curve, so we don't want that one. So, okay. So now what changes when we use them for post-quantum crypto? So we don't want to use discrete log because that is not secure against quantum computers. So what do we want to do instead? Well, we're going to use now a very large set of elliptic curves. We're going to use an exponential size set of elliptic curves, and we're going to look at the maps between them. So those are the isogenies. So that's where the isogeny base comes from, the maps between the curves. And so now we have our elliptic curve from before, and now we're letting A and B range over values in FQ and looking at the curves that we get. And but now we're also interested in maps between them. So these will usually be denoted by phi, a map from one curve to the other that preserves certain structures. In particular, it's a group homomorphism. So it maps the point at infinity, the identity element on the first elliptic curve, to the point at infinity of the second elliptic curve, and is phi of p plus q is phi of p plus phi of q, and it's also what we call a morphism of curves. So that's the map between them. And so the one submission was broken, but there are still many other left. Jason had mentioned Seaside, and there Gabriel had mentioned a few other ones, and so Scallop and like several other ones as well that are still perfectly secure. So now one could sort of say, well, if stuff was broken, why would we even like still want to look at these elliptic curves like isogeny-based crypto at all, it's also, it turns out it's not very fast. So maybe this is just not a good idea to use isogenies-based crypto. So why would you still want to do that? When I sort of listed what types of things were proposed for as a post-quantum secure system, I didn't leave that much out. It's basically code-based system, lattice-based system, and like there's an isogeny-based system, and then there's also multilinear maps, but there's not that much variety. So that means and I think right now, one of the reasons why they asked for more signature scheme is because so many things were lattice-based. I think 3 out of 4 proposals had been lattice-based. So that means if someone comes up with a quantum algorithm to break the underlying hardness assumption, then there's like almost no alternatives left. So that means we really have to consider all the possible candidates. We have a lot of infrastructure already in place because we've used elliptic curves in the context of cryptography already. So it's easy to like implement this and run a bunch of trials to see how hard something is. And then also some computational assumptions that are coming up in the security analysis of the isogeny-based systems, like the endomorphism ring problem, have already been studied classically, and that's like a good thing because that means we have much higher confidence that some problem is hard. If it's only been introduced like 3 years ago, and maybe nobody was really looking at it that much, it's not too surprising that it hasn't been broken yet. But if we take like a mainstream problem, then it's different. Then we have sort of more confidence because I don't know, there's like books about endomorphism rings and stuff like that. Okay, the cons are also plenty. One is that the only submission to NIST was broken. So this might lower the confidence in other systems. And it initially, I think, sort of people were saying, is isogeny-based crypto dead? That was like on like some blogs or some panic people. And then the other thing, if you work with lattices, you of course love that you can do fully homomorphic encryption. There's identity-based crypto. None of this functionality is there with the elliptic, with the isogeny-based stuff, and it's not that someone hasn't found it. It looks like it's just not. It seems unlikely that it would be possible to build that on it. So it has fewer functionalities. And so here are the things that, this is the one that's still hard, and this is the one that we're not looking at anymore. So let me just give an example here. So since I've talked about elliptic curves and isogenies between them, so let's take an elliptic curve like this, a second elliptic curve like that, and so we have some point on this curve that phi maps to the other curve. So that's my isogeny. And in this case, I can just write down what it is just to like sort of see what an isogeny looks like. It's what we call a rational function in x and y. You can sort of, so you plug in your x and y coordinates of your starting point on the curve E1, and then you get a point on the second curve, E2. And I'm drawing a continuous picture. If you did this over a finite field where there's no ordering, then you wouldn't get this nice picture that you get when you just draw a real picture over the reals from it. But okay, and so Gabriel had already mentioned that there are graphs involved here, and so we have pathfinding problems that you could just define in arbitrary graphs. Namely, if you have a graph and I give you 2 vertices, I could just say find a path from vertex S to vertex T. And the graph could be directed or undirected, but so in either scenario, this problem makes sense. And so we're going to look at this particular problem when the graph in question is the supersingular L-isogeny graph in characteristic P. I think someone who had like maybe looked at a paper I was writing or like a talk I was giving, they said there must be like a nicer way to name this object than this like really clunky supersingular L-isogeny graph in characteristic P, but that is sort of that is the name. So there's also, in order to not make the notation too cumbersome, I'm suppressing the P. It's just throughout a very large prime. And so that means I'm only interested in the L here. And so before we're looking into how the graph is defined, which Gabrielle already showed, so let me just say that the graph is exponentially large. And I'll say exactly what that means in a minute. And because the graph is exponentially large, we can really only give an implicit description of the graph. So what we mean by that is I can't like write down an adjacency matrix for the graph, because just writing that down would already take an exponential amount of time. But I can find neighbors of, if you give me a vertex, I can compute its neighbors. It's an expander graph. And in fact, it's even stronger than an expander graph. It's a Ramanujan graph. And the vertices are elliptic curves in characteristic P. And there are like special vertices that correspond to not just any elliptic curve, but so-called supersingular ones, which I'll define in a minute. And so here is a picture of what this graph looks like. So this is the graph GL. It's an L+1 regular graph. So it has like L+1 edges going out. So the L is always very small compared to P, usually 2 or 3. And the graph GL has about P over 12 vertices. And so Y is, you can efficiently compute the neighbors. And what we're hoping is a very hard problem is that if I give you 2 elliptic curves, E and E double prime, it's hard to find the path from one curve to the other in this graph. And so the formal definition is that we're taking as the vertices the elliptic curves in characteristic P up to isomorphism that are satisfying one extra property, namely that they're supersingular. And then we're drawing an edge whenever there's a map of degree L between them. And so that's, L is also the size of the kernel of the map. And so Gabrielle drew a directed graph. And she said that for each edge, there's also, if there's an edge from E to E prime, there's also one in the opposite direction, coming from the dual, what's called the dual isogeny. And here I'm going to be a tiny bit sloppy and just sort of identify those 2 edges and make the graph undirected, which is fine. For example, when P is 1 mod 12, you know, nothing goes wrong. Then that is exactly what the graph looks like. So that means, so this is my graph. And so why is this an exponentially large graph? Well, P over 12, it seems like it's linear in P, but what is really our input size here? Our input size is the prime P, and it takes log P digits to write down P. So that means the input size is really log P. So if I wanted something that's polynomial time, I should really have something that's polynomial in log P. So that means if P has several hundred digits, you're not going to be able to write down the adjacency matrix for this graph. You're just going to define it like this. And so here in the background, I also have this, I don't know if it's visible on the screen. I can't see it from this angle, whether you can like see in the background this large supersingular graph. So it looks very complicated. So if you look at the pathfinding problem in graphs specified to supersingular isogeny graphs, the problem is to find the path from a vertex E to a vertex E prime in this L-isogeny graph that I just defined. So for any vertices that I give you, I want to know what a path looks like. So cryptographic size means several hundred bits. L is 2 or 3 or 5. So the input parameters have size log p. And now if we want to know sort of what are the fastest algorithms for constructing isogenies, those are like O tilde of p to the 1/2. So that's still exponential in p. And so I wrote my slides in Keynote, but it was easier here to display everything with PowerPoint. So the PowerPoint conversion from Keynote to PowerPoint worked almost flawlessly, but the tilde, for some reason, it put up there. And I think I spent 20 minutes in PowerPoint trying to move it down. It would not do it. So I figured it's going to be up there for now. There's going to be a few more of those if you want to look for them. So, all right, so p to the 1/2 up to log factors is the fastest classical algorithm. JF and David Zhao and Sankar used Grover's algorithm to get a quadratic speedup, which gave a quantum algorithm that is p to the 1/4. But those are still both exponential and log p. So that's sort of, and not much has happened since their algorithms. Now, if you actually, so we've all talked about like building cryptography on supersingular elliptic curves, like what does it actually look like as an example. So maybe the easiest in the sense that it takes the least setup. So we fix a point, namely an elliptic curve, in the supersingular isogeny graph where the prime L is equal to 2. So that's just G2. And then we're going to construct a hash function from that. So a hash function takes as an input some message and then compresses it. And in our situation, the output is going to be a vertex in our isogeny graph. And the hard problem is we want the following problem to be hard. If I give you the starting elliptic curve and I give you the output vertex, you can't find the path, i.e. the message. So let me show a picture. So the message that I want to do is 0, 0, 1, 0. And so here we have the 2 isogeny graph. There are some vertices that don't have degree 3 because I stopped drawing vertices. But so we're starting at E0. So that's our first red vertex here on the left. And then we're going, so there is some canonical way to label each vertex either 0 or 1. And we're excluding the one that we just came from so that we're not backtracking. So that means I'm going 0 here. So then the edge that I just used is out. And instead I have 2 other edges, one that I'm calling 0, one that I'm calling 1. I go 0 again, then I go 1, and then I go 0. And so then the output vertex h of m is this vertex right here. And so if you want to, you can call it like the pre-image problem, like what message do I have to put in so that I'm landing at this vertex. So that's the problem that you're trying to solve here. And in complete generality, that's still a very hard, that's a hard problem as far as we know right now. So this is how to construct a hash function from one of these isogeny graphs. But we can also have a different point of view. And in the last part of the talk, I want to talk about that, namely the algebraic problem of the computing endomorphism rings. And you can actually show that pathfinding is equivalent to the endomorphism ring problem, which I'll define, and I'll focus on that and mention an algorithm for computing endomorphism rings with Gabriel Scullard. So, All right, so what is the endomorphism ring? So an endomorphism is just a map from the curve to itself. And the endomorphism ring is just the collection of all those maps. It has a ring structure. So you can now, since everything just goes from E back to itself, you can compose these things, you can add them, you can show that forms a ring. And examples would be just adding a point n times to itself. We call that the multiplication by n map. If you're in positive characteristic, you can raise things to power of some prime. And because of the, and so in positive characteristic, that's again an endomorphism. And then there's a third definition here. And so finally, here is the definition of supersingular, namely, we call the elliptic curve supersingular if the endomorphism ring has rank 4 as a Z module or a lattice. So we always have a copy of the integers in it. So we always have at least a copy of Z. In characteristic 0, that's often the whole story. We might have a second generator giving us something of rank 2. And if there are more maps beyond that, then one can show that the only other option is that the lattice has rank 4. And so that's what we call supersingular. Here is an example. So if I take this elliptic curve, x cubed, y squared equals x cubed minus x, I'm picking a fourth root of unity. You can just think about the curve being defined over C, and then I is actually just I. But it can be over any field, so we're just picking a number whose fourth power is 1, but no smaller power is 1. And then we're going to look at the map from E to itself. That maps a point xy to minus x, comma, I times y. So we're doing this. And we're calling this map bracket I. And the reason for that is that we can check that when we compose I with itself, so we apply I twice, we get what ends up being, it maps a point xy to the negative of the point, which is just minus x comma y. So if the only thing that happens to the point is that the y coordinate gets negated, that's the negative of the point under the group law on this curve. So that means this clearly is not, or maybe I shouldn't say clearly, this is not a map that can be expressed as multiplication by an integer. So that means we have something like z and then an element I that embeds into the endomorphism ring. And if the characteristic of my field that I'm looking at, like for example, if I'm looking at this over the complex number, then that's the whole story, and that's the full endomorphism ring. And if I'm looking at a finite field, and I'm picking P to be 3 mod 4, then I can show that there are more maps beyond the one that I labeled I. So there are more maps than just generated by the integers and that map I. And in fact, as soon as I have things that are outside the structure, from just theoretical reasons, I know that the curve must be in fact supersingular, and so that I have like then 4 linearly independent guys. So this is like an example that shows like it depends on what the parity of P is mod 4, whether or not we get more maps or not, and whether it shows up in the supersingular isogeny graph or not. So if P is 3 mod 4, then one of the vertices in my graph will be this curve E that shows up there. And if it's 1 mod 4, it will not show up in my graph because then it's not supersingular. So it depends on what P is. And so what's the endomorphism ring problem? You give me an elliptic curve, and I'm supposed to come up with 4 linearly independent maps that generate the endomorphism ring as a lattice. And so you can show it's still using under GRH. I have a grad student who was working on seeing where exactly that was needed and where you can remove some of it. But so that is this problem of computing endomorphism rings is equivalent to the pathfinding problem that I showed in the graph, in the supersingular isogeny graph. And again, so here we're hoping that we can somehow leverage the fact that this is already a well-studied problem and something that people are interested in who are not necessarily interested in crypto. So if you tell them like some specific problem, especially if you like specify the torsion information, they would say, oh, this never comes up in any kind of situation that I'm interested in, but computing endomorphism rings is sort of a pretty standard problem to consider. And so now, how can you actually compute these endomorphism rings? One thing you could just do is, well, endomorphisms are maps that start and end at the same curve E. So that means if I think about it in the graph, in the isogeny graph, I'm just looking for cycles in the isogeny graph, because each cycle in the isogeny graph corresponds to a map from E to itself, because it starts and ends at E. So then I could just say, I'll do breadth first search in the isogeny graph and see if I can find some cycles this way. And this was done by David Cole in his thesis. And it's exponential in P, but that was like also it didn't compute the whole endomorphism ring. It found some cycles that generated something of finite index. Then you could also just say heuristically, how many times would I actually have to run a cycle finding algorithm until I get the whole endomorphism ring? And heuristically, you would sort of expect log P calls to a cycle finding algorithm. But that's all it is. It's like a heuristic. So clearly, we have to find one endomorphism that's not multiplication by m and then another one. So if everything uses a cycle finding algorithm, how fast can you find cycles? There is a paper by Delfs and Galbraith from 2016, and the complexity is O tilde of square root p, or p to the 1, O tilde of p to the 1/2, with again the tilde being way up. So that is sort of the fastest cycle finding algorithm that you can plug into any of these other routines like that use cycle algorithms. And then together with Holgren, Travis Morrison, and some other people, we gave an algorithm for a sub-exponential algorithm where if you already have something of finite index, how you can make it bigger and get the whole endomorphism ring. But even that took still a sub-exponential time, and it needed heuristics. So there's still a lot of room for improvement. And but that is the general idea how one can think about solving the endomorphism ring problem, namely that you compute two non-commuting endomorphisms. One other thing that you know is that if the rank is 4, because your curve is supersingular, then your ring that you're looking for is non-commutative. So if you want to get the whole ring, you definitely have to have two non-commuting things in there. And then once you have two non-commuting things, you sort of enlarge it to compute everything. And what I did with Gabriel is that we looked at the second step and gave an efficient algorithm using a factoring oracle that solved that second step. And but it still leaves open the first step, which is only at this point fully exponential. Yeah. Okay, and so the algorithm for step 2 So the main idea is really that we're using our theoretical knowledge of the endomorphism ring, namely that it's what's called a maximal order in a quaternion algebra. So there's a lot of structure there. And the reason why that's interesting is because for these kind of objects, we have a local global principle, meaning we can make changes locally and then get the correct answer for the global object, which is the endomorphism ring. And we can also show that we only have to do it for only finitely many places. So the idea is, if you think about this ring that you're starting with that you want to enlarge, you only have to enlarge it at finitely many places to get the full endomorphism ring. And so this can be quantified exactly by looking at primes that divide the discriminant. And so in order to get your hands on those primes, you need to factor the discriminant. So that's where we need the factoring oracle. And if you have to list all possible candidates for the endomorphism ring, then that takes too much time, and that's why it was only sub-exponential. And there were some extra conditions on there that we needed to guarantee that it was even sub-exponential and that we didn't have an exponential candidate set in that result. And the new result sort of finds the correct enlargement without having to try all possible combinations. So that is sort of the advantage. In this previous result that I was also a part of, we had to construct a bunch of rings and then test, is this the right ring, which can be done efficiently. But in this new paper, we were able to avoid this most time-consuming step. And it uses yet another graph. And so I'm almost at the end of my talk here. So I want to just put a picture up of how you do this locally. You have to find the right object in what's called the Brüher-Titz tree. And so you have some prime q at which you want to enlarge it. So the Brüher-Titz tree looks like this at the prime q. You have your root there that, I don't know, I can barely see it on the screen here. It's the 2x2 matrix ring. It's one of the maximal orders in this complete object that I'm looking at. And then, so this has some nice structure. And so I want to find the vertex in this tree that is the correct enlargement. So it's somewhere down there. And so we have some algorithm of subdividing the tree that lets us sort of efficiently figure out which one the correct vertex is. So there's yet another graph showing up. And so this time a graph that parameterizes what are called maximal orders in matrix rings over complete fields. So another, like a combinatorial object. And so let me just close with some open questions here. So is there anything we can do with a quantum algorithm here? So far, we've seen like square root speedups using Grover's algorithm to compute isogenies, or but not anything that gives us an exponential speedup. So that would be great if we can show that. So, and even as a first step, can we do overall find a sub-exponential quantum algorithm that would solve this problem? And I'm going to stop here. Thank you for your attention.
Thank you very much. Is there some questions for the speaker?